Morning, guys. So yesterday we started into our first kinematics chapter, which is the study of motion. We basically use the lens here of separating our quantities. So far we have some quantities that can be referred to as scalars, and the other type of quantity we can refer to as vectors. Make sure you know the definition of these ones here. Scalars only have magnitude, or they only have size, whereas for vectors, they have both the size, what's called magnitude as well. They also have direction. And we saw a few examples yesterday where sometimes they're the same, especially if there's no change in direction, but very oftentimes they're not the same. Vectors have this arrow above them. Up to this point, we've only studied here distance is a scalar, so d without the arrow. The displacement will be that blindfold analogy. If I'm not actually watching your exact motion, and I just say between when I put on my blindfold to when I take off my blindfold, how far have you been displaced? How far you've been pushed from this initial starting point. We found that the speed is v, again no arrow. The velocity is the vector form of that. Velocity is going to be v with the arrow that way. And we introduce our first kinematic formula here, our basic motion equation. If there is no acceleration, it actually comes from the formula velocity is actually the displacement divided by time. However, on your formula sheet, we would probably isolate that there. We'd actually write it d is equal to v times t. Same formula, but slightly different isolated. Right? Today, we're going to introduce acceleration. Acceleration is actually belonging to this column. Acceleration does have a direction to it. It does actually matter. Am I accelerating to the left or upwards or downwards? We're going to see sort of the interplay with velocity, but the important thing for you to note is these two are separate concepts. We'll see that in this lesson here. There are other quantities as well. If I list, let's say mass. Okay, is mass a scalar or vector? Right. Well, you stand on a scale and you say, well, I weigh 30 kilograms or 40 kilograms, not 50 kilograms north, right? You don't give a direction to it. So there are other examples of scalars here. We're not going to touch on too much just yet, but just hinting at them there. Other scalars include things like mass, right? Time is a really good one. Time is a scalar. Although we do think of time as constantly going forwards, I usually ask myself, can you turn left in it? Can I turn left in time? Can I turn east in time? Well, no, I can't. In this case here, time is actually an example of a scalar. That's going to become super important later on in this chapter here because time actually doesn't have direction. Time is something that can skip over. Time can actually, you might be looking at the horizontal. You find the time here, and time can actually skip over to talk about the vertical as well. Time can actually be the same for both horizontal and vertical. More on that later on. We can talk about forces in our second chapter here. Forces is actually a vector. Forces are pushes and pulls. You can lift an object, so that's a force that's applied upwards. You can push someone downwards, right? So forces are with direction. Energy is a scalar, so heat energy, light energy. Although we can think about sort of sending energy going from one place to the other, the actual energy itself, the number of joules, we're going to do another lesson on another chapter on energy. Energy is actually a scalar. So just to give us a little bit of practice with those basic motion equations here, just for warm-up. Let's start off with a truck. A truck moves from a position positive 20 meters to positive 70 meters in 3 seconds. Then reverses. Again, there's not much variety I can do to the problems so far because I'm just in one dimension. The truck can only go forwards or backwards. It then reverses at 1.5 meter per second, right? So that's going to be a speed. Okay. It then reverses at that for, let's give it 10 seconds. Okay. So a couple ABCs for you to practice here. A, I want you to calculate the speed going forwards. Okay, so for the first part of the motion, right, I want you to determine. They might give you sort of a different keyword every now and then, like calculate, deduce, determine. They're just saying find. Okay, look for that number. Determine the overall displacement and the velocity. Careful, those two there are vectors, so those ones there would need direction. And then C, where does the truck stop relative to the starting line? Okay, and I'll draw you a picture of what I mean. So we have basic setup here. Don't get scared of it when there's ABCs. You can actually use that as a hint. Well, let's do A first, and then A will probably help us do B. Use that as sort of a mind map. So far what we have here, the truck starts off from a position of positive 20. So what I'm imagining here is there's a starting line, there's a flag of some sort. This starting line here would have been 0 meters. The truck actually doesn't begin here. The truck actually starts at positive 20. Positive means in front. So the truck is already at a distance of 20 meters. It must have traveled there at some point before this question. But there it is. The truck starts from there. It then moves to a position of positive 70. Again, measured from the flag. It then moves to a position, now it's actually 70 meters from the flag. How far has the truck actually gone? Remember, the truck was already at 20. It didn't have to travel this 20 when I start the clock. It actually just traveled from being at 20 to being at 70. Hopefully not too hard for you to do here. The distance there is going to be 50 meters, right? 70 minus 20. You take that position minus the early position. If you like a formula, you can go, the change in displacement is basically your d final minus d initial. That delta symbol, we're going to see more in today's lesson here. The delta actually means change in. It's basically a comparison, and it basically says, well, your position at the end was 70. Your position at the beginning was 20. 70 minus 20 means you are 50 meters in front, positive 50. So it does that. It only takes the truck here 3 seconds of time, right? So I start my clock. This is t equals 0. At t equals 3 seconds, it's already made it to the 70. So that's actually going to help me find the speed. And then we're going to deal with the reverse in the next question. So in part A, I want to calculate the speed. Speed is equal to the distance divided by time. The distance that I actually traveled was 50 meters. That's how much ground I covered. It took me 3 seconds of time to do it. This one here will end up being not a nice number here. It's giving me 16.6 repeated. Although we should be using our sig fig rules, like this is a divide, which one is the least precise here. In physics, I'm just going to be a little bit lazy. So in physics, keep all answers to either 2 or 3 sig figs. Now that is usually the case anyways, right? Because most of our measuring tools here are limited. They don't really get into the 4 sig figs, 5 sig figs. But this is just a cheat for us. Even though we actually learned how to do it properly, we actually learn what are the rules when we plus or minus, what are the rules when we multiply and divide. In physics, as long as you keep your final answer as expressed as either 2 or 3, you can say 17 meters per second as well, you won't get marked wrong for sig figs. So that's just a sort of little small cheat. So that is the speed, 16.7. That's actually the velocity as well, because there was no change in direction for that first part of the motion. Now what we want to do is we want to calculate the overall displacement. The overall displacement is not just you going forwards, but it also tracks into the account going backwards as well. So the backward part of the motion here, we're told in the problem, this one here reverses at 1.5. To show you the direction, I'm actually going to add in a negative. Sometimes they give you the negative in the problem. In this case here, for the backwards part of the motion, it then heads in the reverse direction. It then goes at negative 1.5 meters per second. It's actually very slow in comparison to the speed that I already had, right? 16 going forwards, and now I'm like a fraction of that, negative 1.5. But it is backwards, so I'm going to add on the negative, but it happens to do that for a longer time interval. So the clock already said 3 seconds. Between 3 seconds and when the clock strikes 13 seconds, it's going to be starting to head backwards, and it's actually going to sort of lose some of the displacement that I covered. So what I would do here for part B, I would just find what is the displacement. Let's say here's the truck. It's heading backwards. That's why I have my negative 1.5. It's doing that for 10 seconds. What's the displacement just for that second part? Because I know my kinematic formulas, displacement is velocity times time. My velocity was a negative 1.5. We're going to multiply it by 10 here. I can actually show it to you with the units here. Pretty much if we are in SI units, the units are going to cancel out. You'll notice just like the 1.5 times 10 just becomes negative 15. We could go meter per second times something by seconds. The seconds cancel out, and we're left with meters. So as long as everything is SI units, everything will cancel out. So what this is saying here is, in traveling backwards at this slow speed of negative 1.5, in doing that for 10 seconds of time, you're actually going to go backwards. You're actually going to cover 15 meters worth of ground from where you started. So now we basically have the problem done. We had in the first part of the motion, you actually went 50 meters. In the second part of the motion, you end up coming backwards negative 15 meters. So what is the total displacement? The total displacement would be having gone 50 going forwards, and then we're going to have subtract 15 off, and this is going to end up being 35 meters. In total, we did go 50, we ended up in front, we start doubling back on ourselves here. In total, from blindfold on to blindfold off, blindfold on was before your going forward motion, blindfold off is after you came backwards. In total, we are actually only positive 35 meters, right? In fact, we actually went further than this, but because we came backwards, I didn't know that. When I take a blindfold off, you just happen to be 35 in front of where you started. Once you have that overall displacement, it's really easy to find the velocity. The velocity is the overall displacement divided by time. For being pushed 35 meters in front of where you start, it took a total of how long? We did 3 seconds for our first interval, and then an extra 10 seconds. So in total, we actually walked, not a nice number, 13 seconds. 35 divided by 13 gives me here roughly 2.7 meter per second. So this truck here would have had to have had a heading of 2.7 meter per second. You'll notice it never traveled that speed. It was only really traveling 16, or only really traveling 1.5. But if you average it out over the different time periods here, it's like it had gone positive 2.7 really slow speed for 13 seconds worth of time for you to land 35 meters away at 13 seconds. Right? So that's the overall displacement, that's the overall speed. Just to make sure that we're sort of keeping track here, the last question says, where does the truck stop relative to the starting line? Remember, the flag was back here, right? The truck didn't actually start off at 0. The truck was already at 20. So all we're going to need to do is, relative to the starting line, this is actually my true 0. How far does the truck stop in front of that 0? Well, it was 20 meters. That was at the beginning. We now calculate the overall displacement. Having gone forwards and backwards, you're still going to be an extra 35 away. In total, your displacement from the starting line, your total displacement will actually be 20 plus 35. I know I'm sort of repeating, oh, there's a D here, or this is the D that I'm talking about, whatever. Hopefully you can be able to see that based on this, just the picture itself. This is part C. Relative to the starting line, I was already 20 away. There's my 20. You now get an extra 35 away, so then you are at a position, or at a spot of 55. Right? Still basic motion because we are just traveling forwards or backwards. There's no acceleration. In today's lesson, I do want to throw at you acceleration. We actually saw some of these in our toolkit lesson. So let's just start off. Let's make sure we know the definition of acceleration. We already intuitively know what it is. It's sort of like a speeding up or slowing down. Slowing down, we typically call it deceleration, but let me just show it to you how it works out in the math. Acceleration actually describes how quickly velocity changes. Now, the thing that's really weird about this here is velocity by itself was already a change, right? Velocity was distance over time, was a how far do I get divided by how long does it take you, right? That gave us our first basic motion equation. Now what we're doing is we're saying the speed itself might change. You might go from a slow speed and then a faster speed. How quickly you're able to do that change is referred to the acceleration. So let's say you went to buy a car. Usually they give you some statistics. They say, oh, this car here can get from rest. Let's say it goes from 0 kilometers per hour to 50 kilometers per hour, 0 to 50. And this car can do it in 10 seconds, right? Super slow, right? So it goes from 0 to 50. You'll notice that, well, rest means V initial is equal to 0, right? V final, they're telling you it's getting up to 50. It might even get beyond 50, but at least in the interval I'm looking at, it ends up at 50, and it takes 10 seconds to do it. Let's compare it to car B. Car B is also rated here. It's at rest, 0 kilometers per hour. It gets up to 50, right? But it actually takes a much shorter time interval, right? This one took 10 whole seconds before it got up to the speed. This one here actually took a shorter time. Let's make it time of 2 seconds. Let's see if we can calculate between, let's say, car A and car B. We intuitively know, well, car B accelerated faster, but let's see how it works out in the math here. So let's just start off just straight from the definition. acceleration actually tells us how your velocity changes. So it's going to be a delta v. We're going to see this triangle a lot in this course. That is the capital letter delta, and delta usually means change in. It's sort of a time, it's an interval. So it's a velocity interval. It's a comparison between your ending speed and your beginning speed. So that's your delta v. It's not just your change in speed though. Both cars get from 0 to 50. But what it does here is it actually wants to divide by how quickly this happens. It wants to divide by a time interval. This is going to end up later on as a kinematic formula, but let's just deal with this first. So let's find the change in speed here. So my acceleration for these two cars here, whenever you see change in, delta v is just v final minus v initial. Delta is this sort of comparison, is this interval. It's always going to be what is your speed at the end minus your speed at the beginning. It's an ending minus a start. So if I just wrote that out here, acceleration v final minus v initial divided by t final minus t initial, right? Every time I see change, it's just going to be the final quantity, the ending value minus the starting value. Here's where I get my 0 to 50. Again, a typical car manufacturer would actually use the speedometer. So I should be like 50 kilometers per hour minus 0. And I said it took seconds here. So I'm going to get a strange set of units, but just to give you something to compare, it does that in 2 seconds of time. Just going to keep track of my units here. What I have here is a funny set of units. My acceleration is going to have increased. You are now 50 kilometers per hour faster, and it only took you 2 seconds to do it. We now have a really strange set of units here. We're not going to do this unit, but we have a 25. It's like speeding up 25 kilometers per hour, but that took you 1 second to actually change. You do that for twice, and then it speeds up by 50. Let's compare that to the other car. This was the one with the faster acceleration. The other car also goes 0 to 50. Again, unfortunately, I have sort of 50 kilometers per hour like that. I'm going to divide it, but the other car took 10 seconds to actually get up to that. In total, you still have increased by 50 kilometers per hour. But this one here took you 10 seconds of time to do it. 50 divided by 10 is only a 5. You do increase by 5 kilometers per hour for every second that you travel. It's sort of like me saying 5 kilometers per hour faster for every 1 second. If I just do a little bit of math here, I can rewrite that here. 5 kilometers per hour. It's like multiply by the reciprocal, multiply by 1 over 1 second. And that's why I can actually put the seconds just directly right beside it. And that's why I would actually list it 5 kilometers per hour for every second that you travel. Again, this is a very strange set of units. I wouldn't normally do this, but again, let me explain in words for you here. So you go this number, 25 or 5, that many kilometers per hour faster after each second. So for example, for the first one, it only took you 2 seconds and you're already up to 50 kilometers per hour. After 1 second, you're 25 faster. After 2 seconds, then you're 50. That makes sense. What if other one here has a smaller acceleration? It's only 5. So after every second, you only have 5 faster than you were to begin with. So after 1 second, you're at 5. After 2 seconds, you're at 10. It's going to take you 10 seconds of time before you get up to 50. Both of them have acceleration. Both of them accomplish the same change in speed. But because the first one accomplished it in a much shorter time frame, we would say this first one here has a much higher acceleration, has a bigger acceleration than the bottom one there. So in that case there, we can basically deal with acceleration as a change in speed. I'm going to do it for you back in a regular set of units, so it makes a little more sense. What I'm going to do here is I'm actually going to derive for you our second kinematic equation. I'm going to start off with the formula that we just did. Acceleration is a change in velocity divided by a change in time. We just did this manipulation here. Well, change means v final minus v initial, t final minus t initial. Because what's going to happen is my car is going to start, doesn't necessarily have to start from rest, but it's up to me when I set t equals 0. I usually start it when things start moving. Let's say this car here just sat there for 5 hours, didn't move. I wouldn't bother starting my clock. If you tell me, okay, now I'm going to step on the pedal, now I'm going to start accelerating, I'm going to decide to start my clock at that point there. So I'm going to start my t equals 0 when things start moving. That allows me to actually set ti equals 0. Set ti equals 0 to a time that's actually convenient for you. So that t is now gone. What I can do now is I can then multiply the t up. I'm going to get a times tf is equal to vf minus vi. And if you remember in our two-box lesson here, VF is actually equal to VI plus AT. That's actually our second kinematic equation. It comes straight from the definition of velocity, and it gives me a connection between what is your starting speed, doesn't have to be 0, what is your ending speed, doesn't even have to be faster, and sort of how long this process took. You'll notice I have also dropped off the F again. The reason I can do that here is if I start my clock at 0, right? If my clock later on says 10 seconds, if I go 10 minus 0, 10 seconds is the interval. So when you minus a 0, this TF actually ends up being the time interval. So I'm just going to, as long as I know this is the time interval, I can just drop that subscript F. So this is the time interval. This is how long I've actually accelerated for. So this is going to be our second kinematic equation here. Let's just do a quick practice. So a plane speeds up from rest to 200 kilometers per hour in 15 seconds. I want you to calculate the acceleration. Okay. I again gave you a situation where the units are a little bit weird. I'll show you us converting to the proper units and then show you how this works out. So as always, if I can start off with a picture. We start off with a plane. What we know about the plane is it's starting from rest. The VI is actually 0. So the plane is not moving at the beginning. That's actually where I start my clock as well. At this point here, it's going to start accelerating. It's going to start launching its way down the runway. It eventually makes it to a speed. You'll notice the speed here is a positive number. So that would imply the direction for me. It's a forward direction. Forward for me is to the right. This one here, the speed, VF, is actually 200 kilometers per hour. Oh no, kilometers per hour is actually not the unit that I'm familiar with seeing. It's not the SI units. If you look back at the two-box lesson, remember the conversion to meter per second, the correct SI units is a 3.6. If I take 200 divided by 3.6, this will end up giving you the speed 55.6 meter per second. So that's important here. Let me make that note here. Convert all units back into SI before using formulas, just to make sure that the units themselves cancel. Right? So kilometers per hour is really common for speedometers. You just saw that for the 0 to 50 example, but let's convert it back to meter per second because that's more the standard unit. So imagine going from 0 meter per second or 0 kilometers per hour up to 55.6. That's going to be your change in speed. Your VI is 0. Your VF is 55.6. The time interval is 15. Right? So I have 3 out of the 4 variables here. Even if I know the equation, I'm just going to rewrite the equation. You can just borrow this from your formula sheet. VF is equal to VI plus AT. And you're just going to punch the values. Instead of punching in 200, you're going to actually punch in here 55.6. Your starting speed here was actually a 0. Our acceleration rate, I don't know. I don't know how quickly my speed changed every second. But I do know it took you 15 seconds for you to accomplish the speed change. So normally what you would do is you would minus VI over. Minus 0 doesn't do anything. So what I'm actually doing here is I'm going 55.6. I do that over 15 times the acceleration. The acceleration is, keep the whole number in your calculator, divide by 15. My acceleration is 3.7. We're just going to deal with the units here. This 55.6, I'm going to do it on the side. This 55.6 would have had units meter per second. Even after you divide minus 0 seconds, it's still meter per second. I'm going to take this and I'm going to divide it by 15, which is actually in seconds. The 55.6 divided by 15 gave you the 3.7. What happens to the units? We sort of alluded to this earlier. Well, if I take a meter per second and I want to divide it by seconds, it's sort of like multiply by 1 over a second. And that actually elegantly lets me put the seconds together. And we can actually put meter on top all over a second squares on the bottom. So that's going to be our unit. That's the SI unit. Or you can backtrack for yourself. If something is measured in meter per second squared, I'm pretty sure it's an acceleration. Let me just translate in words for you here. You go 3.7 meter per second. One of those seconds is just part of the speed. You go 3.7 meter per second faster after each 1 second. So let me just draw you a quick picture of this one here. We know we were at rest. That's 0 seconds. At 1 second, we're a little bit faster. We're now going 3.7 meter per second. 1 second later. At 2 seconds, we're now traveling 3.7 faster than that. What is that? 7.4. meter per second at 2 seconds. Just like we did in an earlier example, it's not like we're going rest for 0.9 seconds and suddenly we speed up. In fact, we just gradually speed up to that. We go 1 meter per second, then 2 meter per second. It's just that by 1 second, I'm now 3.7. But because I'm now 3.7, the overall distances is now going to slowly increase. So the first d1 here is going to be small, then d2 is going to be a little bit bigger in the next interval, in the next time interval here. If I did that totally for 15 seconds, I would end up with the 55.6 that we have from earlier. That's what we just calculated. We actually cover more and more ground because our speed is getting faster and faster. So that's what it means for acceleration. The bigger the acceleration, the faster your speed changes. Now I want to make one last comment, and then you'll be able to do a lot more of the questions on your worksheet. The whole notion of accelerating and decelerating is this whole notion of when do we speed up and when do we slow down. All right. So in this example, I just want to indicate to you here, first thing, velocity and acceleration are separate concepts. In this question here, my plane was heading to the right. This time, the engines were allowing it to get an acceleration also in the forward direction. After every second, you start traveling faster and faster in that direction. We're speeding up, no problem. What if this plane here were actually traveling backwards? So it actually had a negative velocity. The acceleration could also be in a negative direction. In that case there, I start off at 0. It's like this plane here steadily gets pushed backwards and backwards. Good, that's the direction I wanted to go. In fact, what we're going to have is speeding up whenever velocity and acceleration are in the same direction. If they point in the same heading, either both positive or both negative, we actually have a situation of slowing down whenever these are opposing each other. So let's do the example where the plane is trying to head forwards, right? Little does it know there's a really strong wind that's actually blowing back the opposite way. This wind is going to try to prevent this plane here from taking off here. The wind is actually supplying an acceleration in the negative direction. Now, the plane will probably still take off because my velocity is probably faster than wind. But you notice acceleration is also a vector. Acceleration also has a direction. Just because I'm trying to go forwards doesn't mean the engine is necessarily pushing it forwards. The wind is actually trying to blow it backwards. In this case here, whenever they're opposite direction, we actually will have a situation of slowing down. So whenever our velocity, whenever v and a are in opposite directions, we call that slowing down. In words, we actually call that a deceleration. A deceleration is essentially just a acceleration in the opposite direction. It's like I was trying to head in this direction here, but because of all the wind that's blowing against you, it's actually pushing your way backwards, and we're just trying to figure out what's the speed then. So let's just practice through one last example here. A bike slows to stop, decelerating, that's a negative acceleration, decelerating at 2.4 meter per second squared for 6 seconds. I want you to calculate the initial velocity, the starting speed, and the distance. So as always, I like starting off with a picture if we can. So we have a bike. I'm assuming that it's moving because we're going to have to decelerate. It's going to have some initial velocity I don't know. We have a number here, 2.4. That's meter per second squared, so I'm expecting it's an acceleration. And this is actually a deceleration. It means I'm actually slowing down. So just for convention, let's say this bike here is trying to travel forwards. For me to have a deceleration, it means the acceleration has to be a negative. So I actually need to put on a negative myself. The negative just indicates to me backwards. It's going the reverse direction. It does this for 6 seconds, so gradually it goes a little less far, little less far, little less far, little less far. And it comes to a stop eventually in 6 seconds of time. Sometimes it actually helps just listing the variables. So far I know A is negative 2.4 meter per second squared. Good, it's already SI units. The time is 6 seconds of time. It slows to a stop. So what is my final speed? Well, hopefully you're able to say to me here, well, if I'm at rest at the end, the VF is actually equal to 0. In that case there, I have 3 of my variables. I can look at my kinematic equations to take a look at which formula I can get. So let's try it out here. I'm going to do VF equals VI plus AT. Right? If I have 3 out of the 4 variables, I can solve for the remaining one here. I'll leave you with that question here. See if you can just plug your way through the VF, the VI. You can actually solve for the VI. You're going to find that, yes, I know the overall distance, we're going to travel sort of less and less distance as we go on. But unfortunately, if you look at your equation so far, it doesn't really give you a way to solve it yet. Right? So this is our kinematic equation number 2. So far, we only had one other kinematic equation, which was d is equal to vt. However, the problem with this one here is this one here assumed you had no acceleration. So in fact, in this question here, although we might be interested in finding the distance, we're going to come back a lesson from now to actually give you a new kinematic formula that actually does sort of this displacement formula, and it actually compensates for acceleration as well. So maybe just for simplicity for the time being, just think about how you might calculate distance. We're going to need another formula to solve for that part. Right? So give that a try and keep practicing through your worksheet. You can let me know if you have any questions. Thanks, guys. Take care.